Hi everyone, I'm going to present a system called Ryoan, and it's a distributed sandbox for untrusted computation on secret data. So here is the introduction. Why did I build the system? So data processing service providers often outsource software as a service within their own offerings. However, there is no guarantee that private data such as image editing, text preparation, or health analysis won't be exposed by third-party platforms. One example in this paper is 23andMe, which uses Amazon's machine learning service but faces a tough dilemma. To leverage Amazon's AI capabilities, it must disclose proprietary correlations between health data and various diseases. In these situations, users has no control over their private data once it's handed off to the data processing service. And why can we trust Ryoan? So Ryoan provides three key features to ensure data privacy and security. The first one is the Sandbox. Built on native client, Ryoan confines untrusted code and is compatible with SGX enclaves. The Sandbox restricts both input and output channels as well as covered channels like system calls to prevent unauthorized data leaks. And the second one is trusted hardware. So SGX create an isolated execution environment, which is called enclave. The processor hardware keeps unencrypted data on chip while encrypting it when stored in RAM. The hypervisor and operating system can still manage memory, but they only see an encrypted version of the data. Additionally, integrity is preserved through a collision-resistant hash, is to improving the system security. And finally, there is a confined code module. So Ryoan can configure to allow confined module to communicate in a highly controlled manner. It uses a request-oriented data model, ensuring that data is processed only within a specific enclave, never persistently stored or shared. Every access or modification requires a new request, preventing unauthorized data reuse. Next, I'm going to introduce the SGX security guarantees. Before we dive into Ryoan's security model, it's important to understand its foundation entails SGX. The entire security of Ryoan starts with SGX. So let's first explore how SGX provides a secure processing environment. First, SGX established what we call an enclave, which is a protected memory region inside a CPU. This enclave is completely isolated from the operating system, the hypervisor, and any other applications. Even if the OS is compromised, it cannot access the enclave's contents. Additionally, all data stored in RAM is automatically encrypted by prevent unauthorized access. Then, when an enclave is created, SGX computes a cryptographic hash based on the enclave's code and initial data. This hash acts like a fingerprint for the enclave. If anything inside the enclave changes, the hash will also change, making tampering immediately detectable. So now, before sensitive data is processed inside Ryoan, users need to ensure that they are communicating with a real unmodified Ryoan enclave. To do this, the user requests attestation from SGX. The enclave will then present its hash, which is compared against a trusted reference. If the hash match, it means the enclave was properly created and hasn't been tampered with. This step is crucial because it establishes trust before any private data is shared. So then go to the secure execution. Once the enclave has been verified, it is allowed to retrieve encryption keys from a trusted key server. These keys are necessary to decrypt private data, but they are never exposed to the host system, not even to the operating system or hypervisor. Finally, even though the OS and hypervisor are responsible for managing memory, they can only see encrypted data. The actual decryption and processing happen entirely inside the enclave, ensuring that sensitive information remains protected even if the host system is compromised. So next is the limitation. There are two different parts of the limitation, so all these issues are not flaws in Ryoan itself, but rather vulnerability in the hardware it relies on. So for hardware security limitation, SGX page fault, currently privileged software can manipulate an enclave's page tables, allowing attackers to track memory access patterns at a page level. While this information may seem coarse-grained, researchers have shown that it can be used to reconstruct sensitive data, such as words in a document or even images. And the second is address bus monitoring. SGX does encrypt data in RAM, but it doesn't encrypt memory addresses. This means that an attacker with access to the address bus, for example using a sniffer or a modified RAM chip, could observe which memory regions are being accessed, forming a cover channel at the cache line level. The third one is processor monitoring. Modern CPU have performance monitoring units that provide extensive performance counter information for on-chip events. If the PMU is updated about events that occur in enclave protection execution, then the operating system could use the information as a cover channel to learn secret via untrusted code that could modulate its behavior. And the fourth one is cache timing attacks. Cache timing attacks allow attackers to observe how data is accessed in shared CPU caches. Even when processes do not collaborate, an attacker can extract encryption keys or other secrets by carefully analyzing cache access patterns. And the fifth one is transient execution attacks. There are two different types of attacks, is Meltdown and Spectre. These attacks exploit how modern CPUs speculatively execute instructions to leak sensitive data through microarchitectural side channels, like primarily via CPU caches. So Meltdown is an Intel-specific attack that lets user-level code read arbitrary kernel memory by leveraging out-of-order execution. And Spectre is more general and affects Intel processors. It allows an attacker to read memory from another process's address space by manipulating the branch predictor. So Ryoan mitigates Meltdown using Google native client, which restrict memory access to a 4 GB range that never overlaps with kernel addresses. This prevents Sandbox code from issuing the kernel memory accesses required for Meltdown. As for Spectre, native client also makes it harder to execute, but it doesn't eliminate the risk entirely. It forces Sandbox code to be position independent and limits indirect branches, reducing an attacker's ability to train the branch predictor. And for SGX specific limitations, as you know, SGX is a hardware-based trusted execution environment that aims to protect the confidentiality and integrity of data. However, there are still challenges related to its security assumptions. Specifically, SGX assumes that while the OS and hypervisors may be untrusted, they still control key resources such as persistent storage and network communication. First, let's talk about rollback attacks. While SGX ensures that stored data is both confidential and integral, it doesn't guarantee freshness. which means it doesn't prevent the use of old data. So this leads to a serious issue. A malicious platform like the OS could potentially roll back an enclave's persistent state, restoring outdated data. The enclave itself has no way to detect this, which could result in vulnerabilities or incorrect behavior. Next, we have enclave indistinguishability. SGX allows the platform to run multiple instances of the same enclave, which sounds like a useful feature, but it comes with a drawback. Remote user cannot differentiate between these multiple instances, and while SGX can prove an enclave's legitimacy, it cannot stop a compromised platform like the OS or hypervisor from cloning the enclave. This means that malicious actor could deploy several identical enclaves, manipulating communications between them and tricking remote users into thinking they are interacting with a single instance. Next is the application limitations. The first limitation is limited memory. Since Ryoan is built on an enclave-based system, it's bound by the enclave page cache, which means it doesn't have a ton of memory to work with. This is why Ryoan isn't suited for handling persistent storage. Once a module has seen sensitive data, Ryoan won't let it write that data to storage, helping to keep things secure. Next is network metadata exposure. Ryoan does a great job secure user data, but it doesn't protect things like the user's IP address or the length of network packets. So while the actual sensitive data is safe, the network details like who's communicating and how much data they are sending are not hidden. So another challenge Ryoan faces is with repeated computations on similar or same input data. Essentially, if a service is repeatedly processing the same or similar data, like with online photo services where users keep reading and editing their photos, untrusted modules could potentially observe these interactions over time. With enough repetition, they might be able to figure out sensitive details about the data just by watching how the enclave behaves. So this repeat access could end up leaking information, which is definitely a concern for certain services. Now on the point of multi-user computation, Ryoan does allow batch processing, but here's the issue. If a request involves data from users who doesn't trust each other, Ryoan might not be able to properly keep their data separate. Since Ryoan tracks data at the request level, when multiple users' data get mixed in a single request, it's tough for Ryoan to isolate their secrets. This can create problems if the users are highly distrustful of one another because Ryoan doesn't have the granularity to ensure full separation in such cases. And next is the native client. So Google Native Client is a sandbox that runs native code within a restricted environment. It uses a technique called software fault isolation to keep everything safe. Here is how it works. Disassembly and validation. When you load a native client module, it first breaks it down into assembly instruction. This step is done by a verifier which checks the code to make sure it's safe to run. After breaking it down, the verifier then ensures that everything looks good and safe. The main goal is to make sure the code cannot break out of the sandbox or do anything dangerous that could mess with the system. Now, when the code tries to make system calls, native client doesn't just send them directly to the OS. Instead, it intercepts those calls and decides what to do with them. This way, native client can keep control and prevent any information leaks or unauthorized access to sensitive data. While this setup definitely improves security, it also limits flexibility. because native client is carefully controlling everything. It's not as free to let code interaction with the system in the usual way, which can be restrictive for some use cases. Next is the design. So Ryoan is a distributed sandbox that executes a directed acyclic graph. It's also called DAG, of communicating untrusted modules that operate on secret data. So here is a sandbox instance. From the outmost to the innermost layers, the structure consists of SGX, enclave, sandbox, and module. The privileged software includes the operating system and optionally a hypervisor. The trampoline mechanism ensures that control transfers only to secure memory addresses rather than arbitrary or attacker-controlled locations. A principle, such as company providing software as a service, can contribute a module that Ryoan loads and confines within the sandbox. The setup allows the module to operate on secret data securely, preventing unauthorized access or leaks. So the root of the whole secure system is based on the hardware SGX. The first enclave the SGX creates will be called master. A master enclave creates all sandbox instances and they establish cryptographically protected communication channels among themselves, as specified by the user. Once the distributed topology has been established, the master forwards the attestations for each node in the topology to the user who verified that the configuration matches his or her specification. Then the user inputs his or her secret data. Ryoan provides simple label to protect secret data added by module in the DAG. All of Ryoan's sandbox instances together form a distributed sandbox that protects secret data from being leaked by the untrusted module that operate on it. Also, there is a trail called Ryoan Data Audit Trail. As data moves through the DAG of modules, Ryoan keeps track of which module process each piece of your work. This creates an audit trail that users can access as part of the DAG's output. Although Ryoan cannot verify that modules are performing their intended or claimed function, an audit trail can still be useful. So whether a user wants the audit trail and for what purpose is depends on the application and the user. Next is how the system protects module provider secrets. Ryoan uses public keys as module labels to ensure security when collaborating with different service providers. When a module reads user data, its output is passed to the next module with a union label, which includes the encrypted processed data and the module's previous label. This helps track data flow and ensure the next module is authorized. Module with the same tag can remove the label when needed. If data needs to be stored, the SGX sealing feature is used. The data is passed to Ryoan, which adds metadata and the module's key as a seal, ensuring it can only be accessed by a specific module. So here is the figure 4. Alice's input is labeled with her tag. When the first 23andMe module processes it, it adds its own tag to ensure its secrets don't flow back to the user before passing the data to Amazon's machine learning module. This step is crucial since the user controls the data flow. Later, the second 23andMe module removes its tag from the data label. Essentially, 23andMe public key acts as a group identifier, and both of its modules are part of the group, verified by Ryoan because they are signed with the same key. Ryoan is also responsible for removing the user's tag when securely communicating the data back to the user. Here is how the system optimizing module reset. So since the system is highly secure, it can lead to some time and memory space overhead for the modules. One way to handle this is through a checkpoint-based enclave reset. This method records the module's last execution state, so when it runs the next time, it doesn't need to initialize again from scratch. Another approach Ryoan uses is allowing batch requests before a reset. This way, the same data source can be processed together, reducing the overhead of resetting after every individual input. And the figure shows that the optimized lifecycle and the checkpoint-based lifecycle. Next is how Ryoan balances security and flexibility in the confined environment. So when a module receives secret data and enters the confined enclave, it loses the ability to communicate with the operating system. To handle this, Ryoan provides system APIs. One of the key services is the in-memory virtual file system, which lets modules preload files, making file reading faster. Ryoan uses POSIX compatible APIs to load files into a directory, and any changes made to those files are discarded when the module is destroyed or reset. Another service is Mmap. Before running the module provider has to decide how much memory it will need. This memory size must be determined in advance and cannot be changed later to ensure memory is not overused and that the input data is only processed once, following the Ryoan's request-oriented model. If an application requires a larger database that doesn't fit in memory, Ryoan can break the task into smaller pieces and use different modules to process each piece separately. Protecting Ryoan from privileged software. Iago attacks exploit operating system functions like open and read to attack an enclave. For example, a malicious operating system could return a faulty memory address in read, causing a system to crash. To prevent this, Ryoan uses its own Ryoan library C, which track virtual memory areas to control which parts of memory are readable or writable. SGX has a specific process for verifying enclave memory mappings. First, the module requests memory for the operating system through Ryoan library C. Second, the operating system assigns the requested memory pages and sets the permissions. Third, the module resumes execution and passes control back to the enclave. Finally, the enclave uses an instruction called eAccept to verify that the assigned pages match SGX requirements, ensure they are 4 KB protected frames. To modify memory permissions, enclaves use two instructions, EMODPE, which means enclave modify page permission enable to make pages more permissive, and EMODPR, enclave modify page permission restrict to make them less permissive. However, only enclave code can increase permissions, while only privileged software outside the enclave can restrict them. Besides, Ryoan protects secure communication between enclaves by using temporary encryption keys that are never stored, preventing attackers from instantiating multiple enclave copies to extract secrets. This section explains 4 scenarios where Ryoan provides a previously unattainable level of security for processing sensitive data. For all examples, the Sandbox instances could execute on the same platform or on different platforms, such as the entire computation might execute on a third-party cloud platform like Google Compute Engine, or a provider's module might execute on its own server. Ryoan's security guarantees apply to all scenarios. So Ryoan ensures secure data processing for applications that handle sensitive information. In email filtering, it prevents service providers from seeing email content while scanning for spam or viruses. Personal health analysis like 23andMe use Ryoan to securely run machine learning on genetic data without exposing proprietary insights to third-party platforms like Amazon. Image processing benefits from Ryoan's strict security labels, ensuring images are processed without leaks. And then the translation services use Ryoan to protect confidential text while allowing secure AI-based translation. All these applications follow a DAG-based execution model, where each processing step happens in a confined and controlled environment. So how does Ryoan perform? The biggest source of overhead comes from sandboxing, encryption, system code restrictions, checkpoint restore, and SGX operation, all necessary to keep data safe. To measure the impact, the team tested Ryoan on SGX processors across different workloads. Email processing had moderate slowdown due to frequent system calls. Health analysis suffered the most with 100% overhead thanks to constant encryption. Image processing fared better, like 18% overhead, since computation was the main bottleneck. And translation services, however, took a hit due to SGX memory limits and data transfers. One way to optimize performance is checkpoint restore. It helps avoid full reinitialization, but still adds 55% overhead when resetting modules. SGX memory constraints and frequent e-enter and e-exit calls impact short-life tasks like classification models. Figure 7 shows that the sandbox itself is not the major bottleneck. SGX memory constraints and initialization costs are most significant. Although the performance cost, Ryoan delivers strong security guarantees without relying on trusted service providers, making it ideal for secure distributed computing. Here is the end of my presentation. Thank you everyone for your listening.